This is screencast number 2 from chapter 3. And as I make this recording, it is July 4th. Just a little bit of commentary on this day that we celebrate. In order to have freedom, several things have to be in place. In order to have true freedom, freedom of religion, freedom of speech, freedom of press, freedoms like that, you need to have a strong moral framework and people on board with that moral framework. That moral framework needs to include the idea that all human beings are made in the image of God. We hold these truths to be self-evident, that all men are created equal and endowed by their Creator with certain inalienable rights, among which are life, liberty, and the pursuit of happiness, from the Declaration of Independence. These freedoms are what bring about prosperity in a lot of different ways. Remember, the prosperity is what enables us to support the arts, such as art museums and symphonies and all kinds of cultural and historical museums. Prosperity is what allows us to devote a lot of our resources to scientific investigation and inquiry. Prosperity is what allows us to have a strong defense in order to keep those freedoms. And on occasion, as we've done in this country, to go overseas and ensure the freedoms of other countries. Prosperity also is what gives us the resources in order to provide charity for those who are in need, for those who've suffered a catastrophe or a disaster for whatever reason. And keep in mind that in order to achieve this prosperity and the flourishing that comes with it, human beings need to be free to say, I've got an idea. I think I would like to start this business, this restaurant. I have an idea for an invention. And I think that if I can find somebody to provide me the capital in order to try this out, it might be my own resources, it might be the resources of someone else who is willing to invest. But in order to develop all of these ideas into realities, you need capital, hence the word capitalism. And this capital then allows me to compete in the marketplace of ideas. And that competition, as it goes back and forth between the competitors, is what drives down the price as people figure out better and more efficient ways and cost-effective ways to accomplish their goals. Not only that, but as you become more efficient and as you figure out ways to do things better, you're not using as much resources of energy or raw materials. You don't generate as much waste, and that is what is good for the environment. Think of how much money we've been able to devote in this country to cleaning up our environment so that today we have cleaner air and cleaner water and more trees than we had even a century ago, and even less than that. So I'm very, very grateful to our Lord for our freedoms that we enjoy and the prosperity that comes from that. And I pray every day for our leaders and for our country. All right, there's your little historical backdrop for the 4th of July. Now let's get into our actual lesson. Aqueous solutions. The word aqueous, of course, comes from the Latin word aqua, meaning water. I had 3 years of Latin in high school. One of the best things I took in high school from Mr. Duffy. I remember his name. Very excellent teacher. And because of that Latin, it made my English classes, both vocabulary and grammar, much, much easier. In fact, because of Latin, I think it's one of the reasons I tested out of all English classes in college. Never took a single English class in college. Though I kind of wish I could work it out in my schedule to take literature classes, but be that as it may, it also enabled me to not have any trouble with German the 2 years that I took it in college. because German, like French and Spanish and many other languages, have a lot of words that are based from the Latin. Latin, of course, was one of the languages spoken during the Roman Empire, and Jesus Christ and the disciples and the Jewish people during the New Testament era were very much aware of the Latin language along with Greek and Aramaic. So aqua meaning water. And so it's amazing how many things can dissolve in water, which makes the earth a very amazing place. Number one, because it has water in its liquid state, and because it has water in its liquid state in abundance, which can only happen if you have a predominant environment that is in a narrow range of temperatures. You don't want temperatures ever to reach boiling, where the water would boil off into the atmosphere, and you don't want temperatures to be all over the globe all the time below freezing. So as long as you're between 0 and 100 degrees Celsius, you can have this liquid water. Not very many planets are the right distance from their star and have the right kind of atmosphere in order to sustain water in its liquid state. And then we have all of these minerals, thousands of minerals, perhaps upwards of 5,000 minerals, way more than any other planet that we might be able, as far as we know, in our solar system. And these minerals all serve various purposes. And certainly some of the purposes of these minerals we haven't even discovered yet. But this, of course, is one of the things that makes this planet remarkable for supporting life, but also supporting intelligent life, and not just intelligent life, but intelligent life such as ourselves, who want to discover, who want to build and create and investigate and look into outer space. This is an amazing planet that we live on. So we have all of these different aqueous solutions. We have them in the oceans and lakes and rivers. We have aqueous solutions in our body, thinking of our bloodstream, for example. We have aqueous solutions in all kinds of foods. So these are very, very common. We have other kinds of solutions as well. There are solutions of gases, there are solutions of solids, but we have these aqueous solutions. And in the vocabulary of solution chemistry, which is most of what we do in first-year chemistry, college chemistry is aqueous chemistry. These solutions are homogeneous as opposed to heterogeneous, if you remember your first-year honors chemistry class. And the thing that we're dissolving is called the solute, and the water in this case is the solvent. There can be lots of other solvents as well, various organics like alcohols, for example. But here we're talking about water as our universal solvent. When we use the word universal, we do not mean that everything dissolves in water. That would not be good, because if sand were to dissolve in water, we wouldn't have any beaches. And if rock were to dissolve in water, we wouldn't have any mountains or crust. But so many things dissolve in water, we call it a universal solvent. And we're going to look in this particular screencast as to how the solution process actually works. So, when we talk about aqueous solutions, we can talk about dissolving ionic compounds in that solution or molecular compounds in that solution. And of course, you can remember the key phrase is like dissolves like, which means that the solvent and the solute are alike each other. And what we mean by that is that they're either both polar, have poles, or they're both nonpolar. They don't have poles. And a pole, of course, would be a concentration of negative charge or a concentration of positive charge. And the water molecule, as you know very well, is a very polar molecule. And the polarity of the water molecule is a direct result of its structure. So if we take our oxygen here, and then we have a hydrogen here and a hydrogen there, and they're pushed off to the sides because you have a couple of lone pair electrons. And so these lone pair electrons in this area create a negative region or concentration. And then over here, you've got your hydrogen nucleus, which creates a positive region. And so now you have your polar molecule with a negative and positive pole. Structure determines function. And that you see an awful lot in biology as well. And so this water molecule then, the negative side can yank on positive ions, and the positive side can yank on negative ions. So if you have an ionic compound, depending upon the strength of the force of attraction between the positive and the negative ion, the water molecule has a strong enough polarity to yank apart many ionic compounds. But there are other ionic compounds where the force of attraction between the positive and negative ions is too strong and the water molecule cannot yank them apart, and so that ionic compound would be considered insoluble. When it comes to molecular compounds, if the molecular compound is asymmetrical and therefore has a region that's more positive than the other side of the molecule that would be more negative by comparison, then the water molecule can yank on the positive right up here. The negative side would, and the positive part of the molecule can yank on the negative region of that polar molecule and separate the polar molecules. Again, another part of the dissolving process. So when your ions, for example, become surrounded by little teeny tiny water molecules, we can say that they are now encased in three-dimensional environment by those water molecules. Now, as these ions are moving around in solution, that solution is random. Now, keep in mind, random does not mean that there is no apparent scientific explanation for why that ion is moving in one direction and not another. Random here, as it means throughout a created universe that is obeying the laws and the rules of the creator who established it, means that this motion is very complicated. And there are so many things going on in the motion that it's often very difficult to predict what that motion is going to be a split second later. It's not like the simplicity of a bunch of billiard balls on top of a pool table, where it's pretty easy to predict where one billiard ball will go when it's hit by another. But the more billiard balls you have on there, you might be able to predict the initial direction that a billiard ball might go when the cue ball hits, for example, the 10 balls in a triangle. But the more collisions that go on, it gets harder and harder to predict them all accurately. So keep in mind, the word random does not mean there is no rules or guidelines or principles that are governing its motion. Nothing in all of creation is outside of the sovereign control of the Creator, God Himself. And we can discover and be better and better able at predicting those random motions as we delve deeper into the physical laws that describe these patterns and regularities. And nowadays, as we use computer technology, particularly artificial intelligence, that enables us to be more and more accurate in predicting what's going to happen after 5 or 10 or 15 collisions have taken place. So another jaunt into the world of philosophy. Now, the term electrode here refers to a material that can conduct electricity, such as a metal. And metals, of course, can conduct electricity because the nature of a metal is that it has a bunch of delocalized electrons. You have this matrix of positive nuclei, and these electrons, rather than being held in strong orbitals about each nucleus, are relatively free to move around within the matrix. And those very mobile electrons use this term, mobile charged particles. Those charged particles, by the way, could be ions. But when you have mobile charged particles like electrons, they can carry an electrical charge from place to place near the speed of light through a copper wire, for example. You can also have ions moving through a solution, in which case a solution now can conduct electricity just like a wire can. And we use the word an electrolyte for a solution where you have mobile charged particles called ions. And not mentioned here, but something we'll get to when we get to our chapter in electrochemistry next semester. And that is that you can also have a salt that is so hot, a pure salt, that it melts. And once the pure salt melts, now you have mobile charged particles. For example, if you have liquid sodium chloride, you have mobile sodium and mobile chloride ions moving around. And now it can conduct electricity again. So when you put a couple of electrodes into a solution, you can apply a charge to that solution and force the electrons to go into not the electrons, or the electrons or the ions. You can force them to go in a particular direction, so it's no longer random. In any case, we talk an awful lot more about that when we talk about, for example, batteries and electrochemical cells like voltaic cells and electrolytic cells. So all ionic compounds that are soluble in water are electrolytes. The ionic compounds that are not soluble would not be very good electrolytes. Also, notice that in this equation right here, this equation is not a decomposition reaction. There is a question on one of the tests in AP chemistry, I'm not going to tell you which one, where I ask you to write the decomposition of a particular compound. And some people, when they write that decomposition, they write it as the substance breaking up into its ions. That is not a decomposition reaction. When a substance breaks up into its ions, it is dissolving, which is why we use the AQ here for aqueous. It is dissolving. If I were to take, for example, sodium chlorate, ClO3, and decompose it, metallic chlorates decompose into metallic chlorides and oxygen. You might remember that pattern of decomposition reaction. And we would, of course, need to balance this equation. And so we'll put a 3 there and a 2 there to get 6 oxygens on both sides. And now we have 2 sodiums and 2 chlorides on both sides. That is a decomposition reaction. If I was dissolving sodium chlorate into water, I would get sodium ions, and I would get chlorate ions, and I would have to put the aqueous after each of those things. That is dissolving. So this is decomp, this is dissolving. Make sure you know the difference. It's going to come up. Now, when we have an ionic compound that dissolves pretty much 100% in solution, we say it's a strong electrolyte. And that would mean it's very, very soluble. And that would mean that if we have practically no free ions because they all stay together in the crystalline structure, then we'd have a non-electrolyte. And of course, in between, we would have a semi-electrolyte or partial electrolyte, or more correctly, a weak electrolyte. So looking at this picture, here's your polar molecule. We could also say that this is a positive region and this is a positive region, which therefore would allow this molecule here to connect with the water molecule, this side of the molecule, positive region of the water molecule, connect to the negative oxygen. And up here, we can have a hydrogen, oxygen, hydrogen. And so you can see a single water molecule can actually connect to 3 other water molecules. And in this way, you can actually get crystalline structures like ice or snowflakes. if you only had one region of positiveness, like you might be mistakenly led to believe with just a single positive charge right here, which is actually referring to this whole region, then you just have a big long chain of water molecules and you wouldn't necessarily have ice or snowflakes. In any case, this picture down here shows you a hydrogen atom in the very middle. There's the hydrogen, surrounded by the red negative regions of water molecules, where the red represents the oxygen atom. And if we look over here, this is a chlorine, and you got water molecules surrounding that. And actually, if I look at the pictures up here, this gray part here looks like they're using copper 2+ ion here. So I'm going to erase the hydrogen there and remind us that in this particular picture, this is the copper 2+ ion in the middle, surrounded by water molecules. Keep in mind it's in three-dimensional space. And when we have the dissolving process, we get some interesting math. Did you know that 1 equals 1 plus 2? Well, as long as we're talking about moles or dozens or hundreds, this is true when it's in the dissolving process. For every barium chloride, or dozen barium chlorides, or 100 barium chlorides, or moles of barium chlorides, you get that same number of barium ions when they dissociate 100%. That would be a 1-to-1 ratio. And you get twice as many chloride ions in a 1-to-2 ratio. So remember your stoichiometry when you're showing the dissolving process. And here we have a picture showing a simple way to determine whether an electrolyte is strong or weak or a non-electrolyte based upon its ability to conduct electricity and cause a light bulb to light up. There would be a battery. This is not an voltaic cell, electrochemical cell called a voltaic cell. This is not a battery, but the light bulb would have a battery connected to it. So if I were to draw a battery like this, and let's put the little knob for the positive and negative, we would probably have, this is going to be connected up here. And let's do it a little better. This negative might be connected there, and this wire right here might be connected to the positive. So the only way you can complete the circuit is for these ions in solution to move from one side to the other, completing the circuit to light up the light bulb. That is a very easy way to demonstrate whether or not a solution is an electrolyte and can conduct electricity. In regular chemistry, they do a lab like this. It is qualitative, not so much quantitative. In honors chemistry, and certainly in AP chemistry, we actually use a probe to measure the conductivity, and we get a reading. We get a mathematical reading that can be anywhere from 5 or 10 in pretty much distilled water, all the way up to 20 or 30,000 for very soluble salts. In microsiemens is the unit for measuring this conductivity. So remember that you will be using your conductivity testers in labs in AP chemistry. Now, as a general rule, when it comes to solubility, we usually say that if 1 gram or more, if greater than 1 gram or more, can dissolve in 100 grams of water, we call that solute soluble. If less than 1 gram will dissolve in 100 grams of water, we call that solute insoluble. Notice the word insoluble doesn't mean zero soluble. It means it doesn't pass our definition here, and I should correct that. It's 1/10 of a gram. If less than 1/10 of a gram dissolves, we call it insoluble. And then if you have something in between, and it's not all that common, something between 1/10 of a gram and 1 gram, of the solute will dissolve in 100 grams of water, then we say that it is partially soluble or weakly soluble. So again, as we look at this equation right here, we can see this is not a decomposition, but a dissolving process. We always show that with the aqueous. The aqueous is always going to be used in solution when we have ions that have dissolved in water. Non-electrolytes are defined here. A lot of times your non-electrolytes are non-ionic compounds. There are some molecular compounds that are soluble, such as alcohol, ethyl alcohol. That's the 2-carbon alcohol that looks like this. There's my hydroxyl group. There's my structural formula for the ethyl alcohol. Here is one way to write that in the condensed. That would be the simplest way to write the structural formula, the molecular formula for alcohol, or you could use the condensed structural formula, which would be CH3 and CH2OH would be the condensed structural formula. In any case, water and alcohol are soluble in each other at any level you want. You can have 1 part alcohol through 99 parts water, and 1 part water and 99 parts alcohol. We say they are miscible because they are dissolvable in each part. Miscible. Sugar is also very soluble. It's a solid at room temperature and it dissolves in water. Antifreeze, which is a di-alcohol, if you will. You have 2 carbons and 2 hydroxyl groups instead of just 1 like we had with regular alcohol. This is sometimes called ethylene glycol or 1,2-ethanol diol, where here's carbon number 1, carbon number 2, and it's a diol. Eth means 2 carbons, 1,2 ethana, eth means 2, and the 1 and the 2 are the addresses of your 2 alcohols, and you've got 2 of them, so it's di. You might remember that from organic chemistry. Weak electrolytes are only partially soluble. Now, I should mention something in this formula right here. There are lots of water molecules that don't do anything. These water molecules are only the water molecules that are able to split up and surround these acetate ions. So this is C2H3O2 minus 1, that's the acetate ion. Or you could say we've got 2 carbons, and here's a double bonded oxygen, here's a hydroxyl group. This is acetic acid, and if you take away this hydrogen, now you have the acetate ion. That's what its structure would look like. That's what this is right here. And acetic acid, here's your acetic acid, the condensed structural formula, is only partially soluble. I think it's about 3%, 3 out of every 100 of these molecules dissolve. But there's lots of water molecules. You could add H2O over here and add some H2 over here that don't do anything. And of course, when we write an equation, if it's not doing anything, we don't bother to put it in the equation. So all the water molecules that are not playing a role in this dissolving process aren't shown. And here's a schematic diagram to show you that we have these ionic compounds that become this way, and the non-ionic or molecular compounds that become this way. If these ionic compounds are soluble, then we're going to get strong this would make a solution that's a strong electrolyte. And then our molecular compounds, which includes acids and bases, because remember, an ionic compound is going to be a metal plus a non-metal. And acids and bases do not have a metal and a non-metal. the acid has a hydrogen, and then the rest of the molecule is a anion, and a base has a hydroxide, and then instead of anything else, and then it's going to have a metal right there. But these acids and weak bases are going to come this way if they don't dissolve very much, and hydroxides have a tendency not to be terribly soluble. And there are a lot of acids that are strong acids. By a lot, I say maybe 6. So later when we talk about acids and bases in greater detail, if you memorize your strong acids and you memorize your strong bases, and there's not very many of either, then any other acid or base that you ever encounter is going to be a weak acid or weak base. So by far and away, acids and bases are weak. But strong acids are very, very, very common in chemistry and in industry, like HCl, H2SO4, HNO3. There are 3 of the ones that you're most likely to use and are produced by the millions of tons in industry. All right, so can we come up with some rules in order to make predictions? So one rule that I often talk about is the +1 -1 rule. And that is that if your ion has a +1 or a -1 charge, then the compound of which that +1 or -1 ion is a part is likely to be soluble. And so, for example, you have all these +1 ions in the first column of the periodic table, but also ammonium, very, very soluble ions. You have all of these anions with a -1 charge, very, very soluble ions. You have these halogens that have a -1 charge, very, very soluble. And fluoride gets a separate designation down here just because, interestingly enough, because it's such a small, strongly polar molecule, it actually is not as soluble as the other halogen ions like chloride, bromide, and iodide, and sulfate. But notice all the +1s and the -1s that are soluble. Now keep in mind, the more all-encompassing or generic the rule is, the more exceptions are going to be to that rule. For you should always know that the silver ion, even though it's a +1, is not soluble. And in fact, a lot of your heavy metal ions are often not terribly soluble. Transition metals. So make sure you remember that the silver ion is not soluble, and the exception to that rule is silver nitrate. There's your only soluble silver compound. So that's a general rule of thumb. I often talk about the big 4 of sodium and potassium and chloride and nitrate. Sodium, potassium, nitrate, and chloride as being very, very, very common salts that are almost always going to be soluble. Of course, anytime you want to say the word always, there's probably going to be an exception or two. Now, your insoluble compounds, you might be able to guess that if you've got a -2 charge being attracted to a +2 charge, you've got a much, much greater force of attraction than if you had a -1 charge connected to a +1 charge. And if we think of Coulomb's law of electrostatic attraction, the force of attraction between charged particles is proportional to the charge of one particle, the charge of the other particle, and the distance or radius between those two charged particles squared, where Q could be a positive or negative charge, the other Q could be a positive or a negative charge. And obviously, if your numerator with the Q's in it has bigger charges, you're going to get a bigger force of attraction or repulsion. But if it's a force of attraction, it's going to be harder to dissolve the that particular salt. And you also have your proportionality constant called Coulomb's constant, which is another story in and of itself in terms of how finely tuned that particular constant is in this designed universe that we live in. You might notice the similarity to the law of gravity. The universal law of gravity looks like this. Different constant, we use the capital letter G for that. And then we have our two masses. And then again, the distance between those two masses. Notice that charges can be positive or negative, but as far as we know, there's no such thing as a negative mass. All your masses have positive values. So this force here is always attractive, whereas this force can be attractive or repulsive. This value of G is very, very, very small, in the order of 10 to the minus 11th. This value of K is in the order of 10 to the 9th, if I remember correctly. And so the difference between this force and this force is about at least 10 to the 20th. So you can see that the electrostatic force of attraction here is much, much, much greater than the gravitational force of attraction. Of course, when we talk about the particles being attracted to each other by means of gravity, we are thinking of huge, gigantic particles like planets and stars. All right, so moving right along, if we look at these solubility guidelines then, in this example 3.2, you'll notice there's one of the big four. There's one of the big four right there. They're also both +1, -1. We have +2, -2. Here we have +3, -2. Here we have a +2, and it's a nitrate, which is a member of the big four. So we would have to say this is going to be soluble. This is going to be soluble because of the presence of the +1 or the -1 ion. Or we could say because of the presence of one of the big four. And then by big four, you might even want to add ammonium and acetate and talk about the big six. So if you're walking along the street and you get accosted by Al-Qaeda and they say, here's a formula for an ionic compound, is it soluble or not? And rather than panic and worry and wonder where Homeland Security is, all you need to do is look for a member of the big six or look for a +1 or -1, and chances are you're going to be fine. Let's see here. Let's moving right along. You can see if we were to do more of checking for our understanding, we got a nitrate as well as a +1. So we're going to say that ionic compound is going to be soluble. Calcium is a -1. Calcium chloride, I should say, and calcium is not a transition metal, so that's probably going to be soluble. We're looking at copper oxide, +2, -2. We'd probably say, nah, not soluble because of the double charge for both the positive and negative ion. And then over here, we've got sodium, a member of the big four. And over here, we've got acetate, so we would say this is probably soluble. You can see how quickly you can do that. Of course, on an AP chemistry test, you would be asked to say which of the following salts is soluble in water. You'd be given a list of 5, and then your possible answers might be a combination of any of those. And so you need to be able to do this quickly if you're going to be able to finish the test in time. All right, the next part of this second screencast is section 3.5, focusing on a particular kind of chemical reaction called a precipitation reaction. And of course, the precipitation reaction is a reaction which makes a precipitate. We call it a precipitate because it falls down to the bottom of your beaker or test tube, or ocean or river or lake or whatever. We're not talking about the precipitation in the atmosphere called rain and snow and sleet or hail. Now, when we think of precipitation reactions, There are other kinds of reactions we're also going to be studying, such as acid-base reactions, reactions which form gases, and redox reactions, oxidation-reduction reactions. So let's just focus in on something about precipitation reactions that it has in common with acid-base and gas-forming reactions, but not redox reactions, is that they are exchange reactions. Sometimes we call them double displacement reactions, DD, double displacement. Think of a square dance where the two members of each pair swap partners. Now, just because they can swap partners doesn't make it a double displacement reaction, because in order for this double displacement reaction to actually occur and not revert back to its original state, you have to have a reason for the reaction to go all the way to the right. And for a reaction to go all the way to the right, the thermodynamic reasons would be you either have to form a precipitate, a solid, which of course in a sense removes that compound from the reaction environment so it cannot go back to the left. Or you have to form a gas. If you form a gas, the gas leaves the reaction environment, assuming the container is open and to the air above, and therefore it doesn't hang around so that the reverse reaction can take place either. Or you have to produce a molecule with a very strong bond, like the water molecule does between the hydrogen and the hydroxide. That's considered a pretty strong bond. But also if you have a weak acid, many weak acids are liquids, and if you have a strong molecule with a strong bond, that also would mean the reaction would be inhibited and unable to go to the left. So this is going to completion to the right. If it's doing both things, we say it's reaching equilibrium. So notice again that precipitation, gas forming, and redox reactions are double displacement reactions, are exchange reactions, and have a reason to take place. Redox reactions do not have a reason for taking place, unless, of course, you're providing an outside source of electrical energy to force the reaction to go in one direction. So if on an AP chemistry test you were told which of the following 5 equations goes to completion, you would look for a redox reaction as one that would not go to completion. Now, in talking about double displacement reactions, but we could also apply this to single replacement reactions, decomposition reactions, synthesis or combination reactions, if you remember your categories from first year chemistry. Whenever we do these net ionic equations, in this case we'll be looking at the double displacement net ionic equations. The first thing is we do is we write out the entire equation. And all of these reactants are soluble in water, so we say aqueous. Remember, all nitrates are soluble, and I actually don't know of any exceptions to that rule. We know that silver chloride is not soluble, so there's my solid. This means this reaction has a reason to go to the right, and therefore will not reach equilibrium. It'll go to completion. It'll be product favored, not reactant favored. And I know all my nitrates are soluble, so I say AQ. So there's my balanced equation, just like you had to do on a test probably towards the end of first quarter in first year chemistry, maybe early second quarter. Then the next thing we do in step 2 is every single species in my balanced equation that I can yank apart thanks to the polarity of water molecule, I'm going to yank it apart. So I look at silver nitrate. Can water yank it apart? Yes, because it's soluble. So I yank it apart into its ions. Then I look at the next species, number 2, potassium chloride. It's soluble, +1, -1 ions. So I take it apart. I take it apart into its ions. Then I look at the third species, silver chloride. And I remember that silver chloride is not soluble. It's going to precipitate out, so I leave it as it is. I don't separate it out. Then I look to the next species in my balanced equation, potassium nitrate. You've got two members of the big four or the big six, and it's a nitrate to boot, so I'm going to split it apart. I'm going to split it up into its ions. Now, the next thing I do, and keep in mind this is what we call the complete ionic equation, and as you get good at this, you kind of do this one in your head. You don't necessarily write it down. And then the next thing you do is you cancel out your spectator ions. So first of all, remember the only thing that you cancel are ions. Do not cancel molecules or solids or gases or anything else. Only cancel out ions. And the spectator ions are just that. They're spectators. They're actually not doing anything. For example, if I have nitrates on the left side and nitrates on the right side, they're not doing anything. So my nitrate is going to be a spectator ion. Think about somebody who just watches TV all the day. They're a spectator, but they're not participating. They're couch potatoes. Pardon the joke. Couch potatoes aren't doing anything, so those potatoes are my spectator ions. Dad joke or teacher joke. They're pretty much overlapping and similar. The other thing we notice is that, lo and behold, my potassium ion doesn't seem to be doing anything either. In solution, when we make them, all the different particles collide with each other, nothing's going to happen, so we cancel them out. So the only thing that's left is my silver ion, and my chloride ion are making silver chloride. Another way to do this is if you were to take silver nitrate and you were to take potassium chloride and this would be Cl minus, and then make a chart like this. Every time a potassium ion and a silver ion would collide with each other in the water solution, they'd repel each other. Nothing would happen. Every time a potassium ion and a nitrate ion would collide with each other to make potassium nitrate, water would just yank it right apart again. Nothing would happen. Every time a chloride ion and a nitrate ion would collide with each other, they'd repel each other. They might not even collide. They would repel each other before the collision. Of course, the speed of collision would depend on the temperature of the solution, and nothing would happen. Every time a silver ion would collide with another silver ion, or a nitrate ion would collide with another nitrate ion, or potassium would collide with another potassium ion, or chloride ion collide with another chloride ion, they just repel. But anytime a chloride ion would collide with a silver ion, they would stick. And because they would stick together, you would get silver chloride. It's another way of looking at it. And so now we have what is called the net ionic equation. I often abbreviate that as the net ionic equation. Now, this should not cause you to think about Bill Nye, the science guy, because he is not a science guy, and he is also more and more a very angry atheist. His early videos in his career were very entertaining and helpful, but he's taken it upon himself now to be very, very critical of biblical Christianity, people of faith, anybody that questions the evolution as an explanation of everything biologically, and so it's sad to see where the direction he's taken his life. By the way, when our net ionic equation needs to be a balanced equation, not just with atoms, not just with ions, but also with charges. You need to have the charge must also be balanced. So on the left side of my equation, I have a +1 and a -1, which equals 0 charge. On the right side of my equation, I have a particle, silver chloride, with a 0 charge. So the charge is balanced. And this just reviews how you write your net ionic equations. And your strong acids and strong bases, and there's about 6 of each that you'd memorize. Your soluble salts are always going to be ionic in solution. And so we talk about strong acids, strong bases, and then I use the word, and to keep the pattern going, strongly soluble salts. Then, of course, we have our weak acids, our weak bases, and our weak salts. Those are not going to split up very well in solution. A weak salt would be weakly soluble salt. So let's just add an extra S in there. And here's another example where the first thing we do is we write our overall equation, and we ask ourselves, does this equation even happen? Is there a reason for this reaction to go to the right? And very quickly we say, oh, with a +2 barium and a -2 sulfate, there is a good chance that this is going to be insoluble because you've got double the positive and double the negative charges. Now, barium sulfate might be a salt that, because barium is on the left side of the periodic table and not a transition metal, it might be worth looking up to make sure on a chart that it is insoluble, and it is insoluble. So now that we know that this reaction does not reach equilibrium but has a reason to go to the right, then the next thing we do is we split everything up that we can split up. We march from left to right. Can we split up barium chloride? Yes, it's a chloride. Split it up into its barium and to its 2 chlorines. Notice that the 2 is a coefficient. The 2 goes from being a subscript to a coefficient because you have 2 separate chlorides. Do not make the common mistake of this, because there ain't no such thing. Then we say, okay, what about sodium sulfate? Well, sodium's a member of the big 4 or 6, and we're going to split it up into its sodium ions. And again, notice that the 2 subscript becomes a coefficient because you have 2 sodium ions. And there's my sulfate. And then we go to the next species, barium sulfate. No, we don't split it up. We keep it intact. Then the next species, sodium chloride. And notice that my coefficient there persists, 2 sodiums and 2 chlorides. And then the final thing we do is we look for our spectators. And we notice that my chlorides are going to cancel out. And by the way, members of the big 4 or big 6, however you want to look at, are very, very common. I don't know what the percentage might be. I wouldn't be surprised if it's 80 or 90% of your spectator ions are probably members of the big 4, big 6. Sodium ions cancel out. So the only thing that's left is my barium, my sulfate, and my barium sulfate. And so if we look at this review and check, we will say which of the following compounds is not soluble in water. And we say, okay, there's a nitrate, that's probably soluble. Over here, the ammonium ion is very soluble. I'm going to go with soluble there. Over here, the sodium ion is very soluble. I'm going to go with soluble. Silver compound, it's a +1, but it's silver. Sulfur's a -2. I'm going to say not soluble for that one. Let's see here. Let's look at number 2. Aqueous solutions of 2 reactants listed below are mixed. And so when we mix these 2 solutions together, we swap partners, and immediately I'm looking for a transition metal. I'm going to get lead iodide as my precipitate. So that reaction is going to go to the right. I'm going to get a precipitate. When I come to the next one, I'm going to get a calcium carbonate +2 -2, which I should know, you should know, that calcium carbonate is the formula for marble, limestone, chalk, not very soluble at all. So I'm going to get a precipitate for number 1, a precipitate for number 2. I go to number 3, and I'm going to see barium sulfate. And that might be worth looking up in order to see whether or not it's soluble, because it's a barium compound. And then when we come down to number 4, we've got silver hydroxide. So that's going to be insoluble, we know. So at least 3 of the 4. And then I'll let you look up barium sulfate to see whether or not it is soluble, which of course is going to determine whether your answer is C or D. If I remember, I think it's insoluble. All right, we'll stop here and pick up with screencast number 3 next time.